Hey everybody, it's Dr. Duncan and I'm here to help you work through the two problems that are assigned with our Competition 2 class. If we're going to get better at understanding the possibilities of competitive outcomes when one species is pitted against another, then we need to learn how to work better with using our Zingies, the graphs that we use to determine those possible outcomes. So we're going to go through two problems today, and these problems are already posted for you in a different file, and by now you should have tried to solve those problems on your own. If you have solved them and think that you are ready to check your answers, keep watching this video. If you're in the middle of those problems and not quite sure what direction to go, watch just enough of this video so that you get a hint for how to move forward, and then pause this video and go back and try to solve the problems on your own, and then watch the rest of the video later. So the bottom line is, don't watch this video first and see the solutions. Do as much as you can to try to figure it out on your own. Okay, for problem one, it's pretty straightforward. We've got two species that are in competition, species 1 and species 2. And I've gone ahead and labeled the axes, the x-axis for species 1 and the y-axis for species 2. Now, we can't go throwing numbers on here yet because we don't know what the competitive impact of each species is on the other. In other words, we don't know what K1 divided by alpha 1, 2 is, nor do we know what K2 divided by alpha 2, 1 is. We don't know what those values are, so we can't graph anything on the chart yet. So to get started, let's figure out what K1 divided by alpha 1, 2 is. Okay, so I've pre-written and have appeared here our little formula, K1 divided by alpha 1, 2. And I realize that looks like it was written by a toddler, but maybe a really advanced toddler, but still it doesn't look so great, but we'll work with it here. Okay, so K1 we know is 100, and we know that alpha 1, 2 is 0.4. So if we do the math, we divide 0.4 into 100, and what do we get? We get a big number, right? We're dividing a big number by a very small number. We get a big number, we get 250. So that tells us right there that on our y-axis, we're going to have to connect the Zingi for species 1 all the way up to 250. Okay, similarly for K2 divided by alpha 2, 1, we're going to divide 50 by 0.3. All right, so a big number again divided by a small number, and that's going to yield us 166.7, which I've conveniently rounded up to 167. So now we have enough information for graphing our Zingis, because we've got hang on, bear with me. We've got both our K1 up here that I've circled and our K2 that I've circled up here, and our K1 divided by alpha 1, 2, and our K2 divided by alpha 2, 1. These are the four numbers that we need in order to draw our Zingi lines, our zero no-growth isoclines. Okay, I've tidied up our math here so that we have a little bit more room to work with. The next thing that we need to do is to start marking out where we're marking out our numbers of species on the x and y axis. Okay, so to begin with, if we know that on the x-axis we're going to have to graph both the 167, and we're going to have to graph the carrying capacity for species 1. So we're going to have to put both of these numbers on the x-axis. So we got to range our values up to a couple of hundred. And I always like to try to have my x and y axis roughly the same dimensions so that there isn't like compression on one compared to the other. As just it's a good general rule for doing any graphing. And so I'm going to also look ahead to the y-axis where I'm going to have to graph, and I'm going to switch colors here to help us with this. I'm going to use, how about green this time? On the y-axis, we're going to have to graph 250 as well as the K2, which is 50. Okay, so given all that, it looks like if we make our origin at 0 and make this point over here about 300, if you look to the lower right and then up at the top left of our graph, make this around 300, then we're going to be in good shape for graphing everything so that it's going to turn out nice and neat. Okay, moving forward and drawing with my little pen here, very awkwardly and slowly, we're going to make our origin here at 0 and 0 for both axes. And we'll make this about 100 here. Oh, this is so slow. And then 200 here. Okay. And wow, that looks great. And then 300 here. Oh, I don't know what that line is. We'll just ignore that. Okay. And then similarly over here. In fact, I'll just pause and do this. Okay. I've got our axes labeled with numbers. Now we get to draw some zinges. Okay, let's start with species 2. And so K2 is 50, right up here. So let's mark out 50 on our y-axis, and that would be right about here. Okay, so I'll write here. I'll write K2. I know. Terrible penmanship. Yeah, that looks pretty awful. But that's K2. And then we need to now draw K2 divided by alpha 21. And we know that that number is 167. So that's going to be, I'll say, about right here. So I'm going to just draw over here K2. So I've drawn over here on the right K2 divided by alpha 21. I paused so I could do that more quickly without you having to watch me in my penmanship, which is so awful. Okay, so now we got our zenji down for K2. I just started with K2 because I had the blue ink lined up on our marker. Now let's line up and do the same thing for K1. Okay, K1 is 100, so we're going to start right here on the x-axis. And then K1 divided by alpha 12 is 250. So I'm going to draw my zenji all the way up here and then boom, hit around 250 or so. And let me quickly magically label those for you. Okay, now I got both ends of the zenji labeled. Now, students often get confused dealing with these zenjis and these fractions because they don't understand them. They try to memorize their way through these types of problems. But there's some little clues that can help you out, that can help you keep your head straight. So I already pointed out well, maybe I didn't already point out. If you look up here at the fraction K1 divided by alpha 12, notice that the number 1 is close to the K. Well, the number 1 should always be close to the alpha. In other words, your fraction that involves K1 should always be alpha 12 and not alpha 21. Just little tricks like that can help you keep straight which fraction is which. The other thing I'd point out that is probably pretty obvious is that, for each of the zenjis, the only K that's involved with either end of the zenji is either K1 and K1 or K2 and K2. So in other words, let me get my switch to a different pen color here. Oops. Let me switch to purple here. You know, on the red zenji, it's K1 on this end, and it's K1 in the numerator over here. So this is just a little trick to help you keep straight, like which fractions go with which zenjis. It's always the K1s should match, and again the first number in the alpha needs to match with the K, and whichever K that is. All right. Okay, so remember from previous videos and also what we talked about in class that what this whole graph is about is really different ratios of species 1 and species 2. Imagine that we are experimenters and we can pit these two species against one another. Sometimes we can have a lot of species 1 and a little bit of species 2, or vice versa, or relatively even amounts, that sort of thing. And that's what this graph space represents within the square. And so what we need to do now is map out these 4 quadrants that have been delineated by the Zenjis in terms of how each species is going to behave in that quadrant. So let's take, I'm going to start out here in the big space here, up in the upper right-hand side. So if we're out in this zone, and hopefully you can see my cursor moving around here, if we're up in this zone, for species number 1, we're in negative territory. We are past the blue isocline, and we are up here in negative territory. So that means that for species 1, the direction of its population change is going to be to the left, because it's going to go closer to 0 because it's in negative growth territory. It is way above its blue Zenji line. Similarly, for species number 2, it's also in negative growth territory because it is way beyond its Zenji and its 0 no-growth isocline. So because it's on the other side of this red line, it's in negative territory. So I've drawn my 2 vectors. One for species 1 is horizontal and species 2 is vertical. And the combined vector, if I can get this right, is going to be down to the left. That means that everywhere out here in this white space is going to be down to the left in terms of how these ratios of species would behave if we were to set up experiments pitting one species against the other. Okay, similarly, in this little quadrant down to the lower left, where you can see the cursor moving, we are in positive growth territory for species 1. So because it's below the blue Zenji, that means that it hasn't reached any limits on population growth, so that a population starting right here, where I'm drawing this little circle, that would be, for species 1, a population size that is equivalent to, what would that be, like about 25 or so? That would be in positive growth territory. Meanwhile, for species 2, at that point, if we go over here to the y-axis, that would be roughly what? 10 individuals, 15, something like that. Doesn't matter. It's below it's below the Zenji for species 2, the blue Zenji for species 2, and it's in positive territory for species number 2. So it's going to be up and to the left. Okay, and so the combined vector sum is going to be up like this, up and to the right. Okay, so now we've got all that to say that in this zone here, beneath the Zenjis for both species, the growth is up and to the right. They're both in any combination of species in this zone down here is going to be positive for both species. Okay, next we need to start marking out the other 2 quadrants that are left in this ratio space for the 2 species. So let's start here in this zone that's on the left. Okay, so for species number 1, represented by the red line and the red Zenji, we are in positive territory here. So relative to species 1 on the x-axis, we are in positive growth, so its movement would be to the right if it started right here. Okay, or any place within the triangle to the left of the red line and against the axes. Now for species number 2, we are in negative growth territory. So notice that we are above the blue line for species 2. We are beyond the amount of resources that can sustain any more growth in species 2. Taking into consideration both the carrying capacity and the impact of species 1 on species 2. So that's going to be in negative territory. So relative to the y-axis for species 2, population growth is going to go down. Okay, and as you probably have already figured out, way ahead of me, as you usually are, the vector sum diagram is then down to the right. Okay? Now already you can probably start to figure out that that we're headed towards coexistence of the two species, okay? But let's confirm that by making sure that we know what our vector sum diagram is going to be like in this little tiny triangle at the bottom next to the x-axis, because that's our final quadrant to map out, okay? So in that quadrant, you will note that we are past the red line. We're past the point where there's resources that can sustain any more growth in species number 1. So its growth is going to be negative, and I got to squeeze all this into this little tiny corner that I made for myself. Good job, Duncan. Okay, and so that left arrow represents negative growth for species 1, and for species number 2, you'll notice that we are below the blue Zenji for species 2, so that means positive growth for species 2. Okay, so that means that its vector sum is going to be, of the two population, the ratio is going to be towards the center of the graph. And so there's our confirmation that we thought through this correctly, and that no matter where we start in graph space here with any ratio of species 1 and 2, it is going to wind up leading to this spot right here in the middle, which is stable coexistence of the two species at that number right there. Okay? Pause there for just a second to switch color here. What I want to illustrate is that we can actually then use, I'm drawing a green spot here now where that where the stable coexistence is. We can use that to make estimates of how many individuals can be supported from species number 2, which is this green line I've drawn to the left, and species number 1, which is down to the right. So approximately at stable coexistence, I'd expect something like about 90 individuals of species 1, and for species 2, roughly, I don't know, 30 individuals or something like that. The important thing is that it's stable coexistence, and the two species can live in the same environment relatively indefinitely because they don't have enough impact on each other to cause the other one to be excluded from the environment. Okay, hope that helps.